Assalamualaikum, my name is Sul Najaf and my roll number is 21TE06. Today I will be discussing lab number 10 of digital signal processing and the lab title is frequency sampling design method. The objective of the lab is implementation of FIR filter using frequency sampling method. Frequency sampling design method. In addition to methods of Fourier transform design and Fourier transform with windowing discussed in the previous section, frequency sampling is another alternative. The key feature of frequency sampling is that the filter coefficients can be calculated based on the specified magnitudes of the desired filter. Frequency response uniformly sampled in the frequency domain. Hence, it has the design flexibility. This is the illustrative usage of MATLAB function FIRFS, and this is the MATLAB program for the FIR filter design using the frequency sampling method. In task number 1, we have been given example 7.13 and we've been asked to design a linear phase low pass filter with 25 coefficients using the frequency sampling method. Let the cutoff frequency be 2000 Hz and assume a sampling frequency of 8000 Hz, and then plot the magnitude and phase frequency response. Now here in this code, Fs is the sampling frequency, N is the filter order that we have set to 25. Then we have magnitude specifications. H1 and H2s are the vector defining the desired magnitude response of two different filters, and these vectors specify how the filter should behave at certain frequency point. Next, we have the frequency vector. F is the frequency vector normalized to the Nyquist frequency, that is half of the sampling rate. It contains equally spaced frequency points from 0 to 1. Next, we have the design filter using FIR2. B1 and B2 are the filter coefficients designed using the FIR2 function, which creates an FIR filter with a specified magnitude response. Then to calculate the frequency response, frequency Z computes the frequency response of the filters H1 and H2 and the complex responses of B1 and B2. F is the corresponding frequency vector. Then for the phase response, unwrap angle H1 and unwrap angle H2 compute the phase response of the filters removing discontinuities. The phase is converted into then radians, from the degrees to radians. From radians to degrees. Then to plot the magnitude response, the first plots the magnitude response of H2 and H1 in decibels. The x-axis represents the frequency in hertz, and the y label represents the magnitude response in dB. For the plot phase response, the second subplot plots the phase response of H1 and H2 in degrees. The x-axis represents the frequency in hertz and the y-axis represents the phase in degrees. Now when we run the code, we observe two subplots. The first subplot is of the magnitude response. The graph displays two curves corresponding to the magnitude responses of the filters H1 and H2. H1 is the dotted line that represents blue. Blue is the dotted line that represents H1, and red is the solid line that represents the filter H2. H1 has a flat response at 1 up to a certain frequency and then drops to 0. And while H2 has a similar response but includes a drop of 0.5 before going to 0. Then the second subplot is the phase response graph. The graph will display two curves corresponding to the phase response of the filters H1 and H2. The phase response shows how the phase of the filter output varies with the frequency. The x-axis will show the frequencies of from 0 to 4000 Hz, and the y-axis shows the phase in the degrees from -2000 to 0. Task number 2, example 7.14. We have to design a linear phase bandpass FIR filter with 25 coefficients using the frequency sampling method. Let the lower and upper cutoff frequencies be 1000 and 3000 Hz respectively, and assume that the sampling frequency is of 8000 Hz. Then we have to plot the frequency responses. Here, Fs is the sampling frequency, which is 8000 Hz, N is the filter order, which is 25. For the magnitude specifications, H1 and H2 are the vectors defining the desired magnitude response of two different filters. And these vectors simply specify how the filter should behave at the certain frequency points. For the frequency vector, F is the frequency vector normalized to the Nyquist frequency 0 to 1. It contains equally spaced frequency points from 0 to 1. For design filters using the FIR2, B1 and B2 are the filter coefficients designed using the FIR2 function, which creates an FIR filter with a specified magnitude response. For calculating the frequency response, frequency Z computes the frequency response of the filters H1 and H2 that are the complex frequency responses of B1 and B2 respectively. Whereas W is the corresponding frequency vector. For the phase response, unwrap angle H1 and unwrap angle H2 compute the phase response of the filters, removing discontinuities, and the phase is converted from radians to degrees. For plotting the magnitude response, the first subplot plots the magnitude responses of H1 and H2 in decibels. The x-axis represents the frequency in hertz, and the y-axis represents the magnitude in decibels. For the plotting of the phase response, the second subplot plots the phase response of H1 and H2 in degrees, and the x-axis represents the frequency in hertz, and the y-axis represents the phase in degrees. Now, if we run the code, we observe two subplots. The first subplot is the magnitude response. The graph displays two curves corresponding to the magnitude response of the filters H1 and H2. H1 has a passband gain of 1 from a certain frequency, followed by a stopband gain of 0. H2 is the red line. It has a similar passband with a transition region at the beginning of 0.5 gain, followed by a stopband with a similar transition gain. The x-axis shows the frequencies from 0 to 4000 Hz, and the y-axis shows the magnitude in dB. Then the second subplot shows the phase response. The graph displays two curves corresponding to the phase response of the filter H1 and H2. The phase response shows how the phase of the filter output varies with the frequency. X-axis shows the frequencies from 0 to 4000 Hz, whereas the y-axis shows the phase in degrees. Task number 3. Find the magnitude response in phase for the following filters, and we have been given several subparts. 7.13. Determine the transfer function for a 3-tap filter, low-pass filter. 3-tap FIR low-pass filter with a cutoff frequency of 150 Hz and a sampling rate of 1000 Hz using the frequency sampling method. Now here we have the cutoff frequency 150, the sampling frequency 1000, and the N is the filter order that is set to 3. For calculating normalized cutoff frequency, normalized cutoff is the cutoff frequency normalized by the Nyquist frequency, which is the half of the sampling frequency. Then the frequency sampling method is where N is the vector representing the sample indices from 0 to n-1. H computes the impulse response of the filter using the sinc function, which represents an ideal low-pass filter in discrete time. Whereas H1 sets the first element of H to the normalized cutoff frequency to handle the division by 0 issues at n is equals to 0. For converting to the transfer function, H computes the fast Fourier transform of the filter's impulse response H and convert it into the frequency domain. For the magnitude response calculates the magnitude of the frequency response, and the phase response calculates the phase of the frequency response. And then we plot the magnitude response and the phase response. For computing the FIR filter coefficients, B assigns the computed frequency response H as the FIR filter coefficients, and displaying the first three FIR filter coefficients prints the first three FIR filter coefficients to the console of the command window. Now when we run the code, we observe that the first subplot is it displays the sum plot of the magnitude response of the FIR filter. The x-axis represents the frequency in hertz, ranging from 0 to 500, and the y-axis represents the magnitude of the FIR filter response. Given that n is equals to 3, the plot have 3 points corresponding to the magnitude responses at those frequencies. Secondly, we have the second subplot that displays the phase response of the graph. The x-axis represents the frequency and the y-axis represents the phase and variance. Similar to the phase magnitude response, the phase plot will also will have 3 points of the phase responses at those frequencies. And then we look at the command window. We have first three FIR filter coefficients. 7.14 determine the transfer function for a 3-tab FIR high-pass filter with a cutoff frequency of 250 Hz and a sampling rate of 1000 Hz using the frequency sampling method. Here we have the cutoff frequency of 250 Hz and a sampling frequency of 1000 Hz, and n is the order of the filter. Then for the calculating of the normalized cutoff frequency, normalized cutoff is the cutoff frequency normalized by the Nyquist frequency. Frequency sampling method, where n is the vector representing the sample indices from 0 to n minus 1, and h computes the impulse response of the filter using a modified sinc function. Then h1 is equals to the normalized cutoff, sets the first element of h to the normalized cutoff frequency to handle the division by 0 issues at n is equals to 0. For converting to the transfer function, h computes the fast Fourier transform of the filter response h and converts into the frequency domain, and then we compute the magnitude response and the phase response, and then we plot the magnitude and phase response. And if we run the code, we see that the first subplot shows the magnitude response using a stem plot. The x-axis represents the frequencies and the y-axis represents the magnitude. We have been given that the filter order is n is equals to 3. So the plot will have 3 points corresponding to the magnitude response at those frequencies. This is 1, 2, and 3 points. Similarly, the phase plot shows the phase response at those frequencies. Now 7.15, determine the transfer function of a 5-tab FIR low-pass filter with a cutoff frequency of 2000 Hz and a sampling rate of 8000 Hz using the frequency sampling method. Here the rest is same as the previous task. The only difference is in the cutoff frequency, which is 2000 Hz, the sampling frequency 8000 Hz, and the order of the tab filter is 5. After running the code, we observe that the magnitude, we have 2 subplots. The first subplot shows the magnitude response, where the x-axis shows the frequency and y-axis shows the magnitude. And we have the order n is equals to 5. So we have the plot which has the 5 points corresponding to the magnitude at those frequencies. Similarly, we will have 5 points that will show the phase response at those frequencies. In 7.16, determine the transfer function for a given 5-tab FIR high-pass filter with a cutoff frequency of 3000 Hz and a sampling rate of 8000 Hz using the frequency sampling method. Here the cutoff frequency is 3000 and the sampling frequency is 8000, then the tab filter is 5. The normalized cutoff frequency is the cutoff frequency normalized by the Nyquist frequency. In the sampling frequency sampling method, n is the vector representing sample indices from 0 to n minus 1. H computes the impulse response of the filter using a modified sinc function, and h1 is equals to the normalized cutoff. Will set the first element of h to 1. To convert to transfer function, H will compute the fast Fourier transform of the filter response H and convert it into the frequency domain. Then we compute the magnitude response, the phase response, and then we will plot the magnitude and the phase response in two different subplots. So when we will run the code, here we have two subplots. The first one shows the magnitude response and the second one shows the phase response. The order is 5, so we have 5 different points at those magnitudes of those frequencies, and the same will be for the phase. But the difference is that we will have the plot of those 5 points for the phase response at those frequencies. Now for 7.17, given in the following specification, 7-tap FIR bandpass filter, and the lower cutoff frequency is 15,000 Hz, 1500 Hz, and upper cutoff is of 3000 Hz. The sampling rate is 8000 Hz, and the frequency sampling design method determine the transfer function. Here the lower cutoff frequency is 1500 Hz, the upper cutoff frequency is 3000 Hz, sampling frequency is 8000 Hz, and the tap order of the tap filter is and it's the filter order, that is the 7, which means that it is a 7-tap FIR filter. For calculating the normalized cutoff frequency, normalized lower cutoff is the lower cutoff frequency normalized by the Nyquist frequency, which equals to 0.375. And the normalized upper cutoff frequency is the upper cutoff frequency normalized by the Nyquist frequency, which equals to 0.75. For this frequency sampling method, n is the vector that represents sample indices from 0 to n-1. H compute the impulse response of the bandpass filter by subtracting the two sinc functions, and H1 is H1 is equals to 1 minus normalized upper cutoff, such the first element of H2 1 minus normalized upper cutoff to handle the division by 0 issues at n is equals to 0. For converting to the transfer function, H computes the fast Fourier transform of the FIR of the filter's impulse response and then convert it into the frequency domain. Then we compute the magnitude response, the phase response, and then we plot the magnitude and the phase response. So when we will run the code, we will observe two subplots. This first subplot shows the magnitude response. The y-axis represents the frequency and the magnitude, and the x-axis represents the frequency. Given that n is equals to 7, so the plot has 7 points corresponding to the magnitude response at those frequencies. Similarly, for the phase response, we have the 7 points for the phase corresponding at those frequencies, and in the command window we have the H. Thank you. That's it from lab number 10. We'll see you in the next video.